Okay, part 3. What we're going to do is try to set up an integral that finds the volume under the whole bowl instead of the chopped up bowl where we made a little Play-Doh piece of fudge. Now, one thing that's going to happen a lot is we're going to have to be able to draw just a nice sketch, decent, of the actual volume. And always we're going to have a bird's eye view, and you're going to see why in just a second. Now, how am I going to do this? I'm going to try to do this exactly the same way we did before. I'm going to start by taking a chop. And from above, we've got our Play-Doh, and I'm just going to take a chop. Not dead center, so I can't say it's dead center. What I want to do is just get a nice little slice so I can see exactly what's going on. So I'm just going to move everything except the slice off. And I just want to find the volume of this one little slice. Now, what is this slice? You can see that it's actually the area under that whole piece of parabola times the thickness. So I'm going to write that down because that's actually what we have so far. I want the volume of one slice. And again, like last time, it's going to be the area of the face, or at least approximately the area of the face. Because remember, this always allows a little bit of lying. I'm saying that the front and the back of this have exactly the same area, which they don't, times the thickness, which I'm just going to call TH period. Now, we sliced like this, and you can see that the thickness is delta x. Like that. The area of the face, like last time, is going to be an integral. Now, what integral are we looking at? We chopped like this, right? So it's actually the y's that's running along. It's going to go from y to z. I let my piece of parabola go all the way down to the axes this time. So it doesn't have the square sides. You can see it looks just like that. And so if I want the area of the face, it should be an integral. It should be the integral under our equation. Remember, when we chopped like this, we were holding basically x constant, right? So x is going to be a constant here. It's y that's actually changing. The problem is, when I do this, I don't know what y values it is, because basically what we did was we chopped like that, and what we need to do is figure out what the y value is there and the y value is there when x is the location of the chop. Well, if x is the location of the chop, what I want to do is I want to know the y value there and the y value there. So I'm going to take my equation like this. And remember, this is the bird's eye view. This is actually in the plane. So what we did is we took the whole Play-Doh model and smooshed it all the way down to the xy plane when the z is 0. And I want to know what the y is. So what I'm going to do is solve for y here. What I'm going to get is that y is equal to plus or minus the square root of 25 minus x squared, like that. That says that the y coordinate down here is negative the square root of 25 minus x squared. The y value up here is the positive square root of 25. That's minus x squared. They should make fingers so that they erase stuff better. Like that. And the area of the face is going to be this integral where the limits of integration are going to very much depend on where our slice is. But meanwhile, we do have an expression now for the volume of one chop, and I'm going to go put that in over here. This is just going to be an integral from minus square root of 25 minus x squared to the positive square root of 25 minus x squared, and then I've got my 25 minus x squared minus y squared in here like this, and this is dy. Because remember, this whole thing in the parentheses is just the area of this face. And we chopped it like that and took it out. Now, in the rest of these problems, basically what I usually do is I call this thing right here, that's the roof, right? And then we smooshed it down and we get this region in the plane. Meanwhile, we have the volume of one slice. We can do better than the volume of one slice. We can add them all up. So I'm going to add them all up. Which will give us an estimate of the volume. I can make that estimate better by making delta x smaller. We can get the exact volume by taking the limit. And I'll just write that out right here. This should be the limit. As delta x goes to 0 of the sum of the integrals. And this is minus square root of 25 minus x squared, like this. This is the square root of 25 minus x squared. The roof is still 25 minus x squared minus y squared. The inside integral is dy. The outside had a thickness of the slice. And when I look at this thing right in here, that really is a function of x. Every time you put a specific x in there, you get a number. So that's actually a function of x. So what I have is, the limit is delta x goes to 0 of a sum, f of x, delta x. That's an integral. We know that from Calc 1 and Calc 2. Now how does the notation work? When you take limits of things with Greek symbols, you replace them by their more modern symbols. So I'm going to get an integral there. I'm going to get an integral here. And again, we're going to rewrite this whole thing in. So I get like this, and I get like this. The roof is still there, 25 minus x squared minus y squared dy. When we took the limit as delta x goes to 0, we replaced that old Greek symbol with a much more modern one like that. And as before, x is just the location of the chops. Now I'm going to repiece this whole thing back together. Just a reminder, yes, that x went all the way back to minus 5 and all the way forward to 5. So I get a double integral that looks like that. Now, what did I really need to be able to do in order to do this? We'll set that up in the next video, but meanwhile, we'll just talk about it just for a second. We need to know what the equation of the roof is. We need to know when we take a chop, when that chop actually enters the smushed region and leaves the smushed region. And when we're done, we need to know the location of the chops from left to right, assuming we're actually chopping that way first. We're going to set up the procedure in the next little video.